We are going to look at a specific type of bilinear form. In this setup, if you take two input vectors and swap their positions, the output exactly reverses its sign. Written algebraically, this means f of xy equals negative f of yx. You can take any generic bilinear form and split it perfectly in half, one symmetric part and one skew-symmetric part. We are focusing entirely on the skew. This creates an immediate constraint. If you feed the exact same vector into both slots, the rule says f of xx must equal negative f of xx. The only number that equals its own negative is 0. Evaluated against itself, a vector produces zero area, or zero projection. We can translate this behavior directly into a coordinate matrix. If the matrix A represents a skew-symmetric form, its transpose must equal negative A. That algebraic rule restricts the layout of the matrix. To equal its own negative, the main diagonal has to be entirely zeros. Meanwhile, every off-diagonal entry must reflect across that diagonal and flip its sign perfectly. Skew-symmetric forms measure pure alternation between distinct vectors. They reject any measurement of a vector interacting with itself. This brings us to a strict structural rule. Theorem 6 states that the rank of any skew-symmetric bilinear form must always be an even number. Geometrically, if you find two vectors alpha and beta, where f of alpha comma beta equals 1, those vectors are inextricably linked. They span a 2D plane that is isolated from the rest of the space. If we extract the matrix representation of just that plane, we get a highly specific 2x2 block. Once we isolate this plane, we can look at the subspace that remains. Because the form is skew-symmetric, any vector left over is either part of another linked pair, or it evaluates to 0. We repeat this process, peeling away two-dimensional planes one by one. The rank is the total dimension of these linked planes. Since each link requires exactly two vectors, and a single vector evaluated against itself is always 0, the rank cannot increase by 1. It only grows in pairs. We also need to understand what happens when linear operators preserve a form. A transformation preserves a bilinear form if the evaluation of two vectors remains constant before and after they move. Algebraically, f of tx ty equals f of xy. We can calculate this using coordinate matrices, applying the transformation m to vectors x and y, and distributing the transpose yields x transpose times the quantity m transpose am times y. This must equal our original evaluation, x transpose ay. This leaves us with a core mathematical condition, m transpose am equals a. Notice the structure. This uses a transpose, not an inverse. It is distinct from m inverse am equals a, which is the rule for changing a basis. Preserving a form is not a simple change in perspective. This condition identifies the specific transformations that leave the geometric measurements of the space the same. According to Theorem 7, the set of all linear operators that preserve a non-degenerate bilinear form constitutes a mathematical group. To see why, test your recall. Try to prove why an operator T preserving a non-degenerate form must be invertible. If we check the null space and assume T of x equals 0, then f of xy equals f of tx ty, which is f of 0 ty, which is 0. Since the form is non-degenerate, x must be 0. The operator is invertible. Let's apply this preservation rule to the standard dot product. Here, the matrix A is simply the identity matrix. The preservation condition becomes m transpose m equals the identity. The matrices that satisfy this equation form the orthogonal group. We can scale this up to something more complex, like the pseudo-orthogonal quadratic form of spacetime. The matrix for this form is a 4x4 diagonal matrix with entries of 1, -1, -1, and -1. The positive entry represents the dimension of time, and the negative entries represent space. The matrices that preserve this specific spacetime form are called Lorentz transformations. When an object moves at high speeds, these transformations warp the measurements of space and time, but they preserve the quadratic form. Because the form is preserved, the boundaries of the light cone, the speed of light, remain the same. The groups that preserve these bilinear forms define the limits of what can change in a physical system. By identifying these algebraic symmetries, we find the transformations that leave the core